Hello, and today we are talking about antiderivatives. What we've done in the past is we started with a function and we've taken the derivative, and the notation, of course, for that is this. The ddx is an action, it's a command. It means take the derivative of y. Now, when we're finding an antiderivative, we're starting with the derivative and going backwards to find the original function. So this notation right here is an action or a command, means find the antiderivative of y. So let's go ahead and find this first one. So find the antiderivative of x squared minus 5x plus 3. So I'm going to start with the x squared. What do I have to start with so that when I take the derivative, I get x squared? Well, I know I'm going to start with an x cubed. And when I take the derivative in my head of x cubed, I get 3x squared. However, there's no 3 inside my green box here for what I want to end up with when I take the derivative. So what would counteract the 3 that I'm going to get when I take the derivative? And that would be a 1/3. So we can either think about it like that, or we can think about it one other way, which would be x to the third. I add 1 to my exponent, and I divide by my new exponent. Either way works to find the antiderivative of that. The next one is negative 5x. So what did I have to start with to end up with a negative 5x? Well, I know that I had to have an x squared, and my constant kind of stays along for the ride, but just like I did that first term, when I had x to the first power in my original thing that I was finding the antiderivative of, I add 1 to the exponent to get 2, then I divide by that same exponent. So moving on to the last term, I have a plus 3. And when I find the antiderivative of that, what did I start with? So when I took the derivative, I got 3. It ends up being 3x. Now, what we want to do is actually, let's check this and take the derivative now and see if I actually get back to the original thing I had. So I'm going to take the derivative just to check. So this isn't actually part of your process except you're checking, unless you want to check every single one. So this is your check. So I take the derivative and I have a 1/3. So I really have a 1/3 right here, which is a constant, which stays. The derivative of x to the third power is 3x squared. Again, I have a constant right here, negative 5/2. That would stay. The derivative of the x squared is 2x. And then the derivative of 3x is 3. When I simplify that, my 1/3 times 3 reduces to a 1, leaving me with x squared. Over here, my 2 and my divide by 2 reduces to a 1. I'm left with my minus 5x, and then the plus 3 is there. And is this the same as that? And it is. That's exactly what we started with. Now, when I gave you the antiderivative, I left something off. And that is right here. We need to take into account that there could be some constant that you add to the antiderivative. So why is that? Well, let's say that I had in my antiderivative, which is this step at the top of my screen, couldn't I have had maybe a plus 7 at the end? And when I took the derivative of plus 7, the derivative of a constant is 0. So technically, there could be some constant right there, and I have no idea what the constant would be, but I know there could be one. So what I need to do is actually write the antiderivative is going to be x cubed over 3, or 1/3 x cubed, whichever way you're more comfortable with, minus 5/2 x squared, or 5x squared over 2, plus 3x, and then I need to say plus some constant. I acknowledge there could be a constant there. There doesn't have to be a constant there, but there could be one there. So I need to put that plus c at the end to say there might be something here, but I have no idea what it is. So this is just acknowledging that. So every time you do an antiderivative, you need to have this constant plus c. I like to think about it in elementary school. You were not allowed to bring in candy for only yourself. You had to bring in candy for everybody. Everybody gets candy. Everybody gets a plus C. So let's look at example 2. So now I've thrown in some trig. Oh dear. So for this one, I'm going to go ahead and rewrite it first. I'm going to pull that 6 right on out. A constant, so nothing with a variable, nothing with an x, but a constant can be pulled out of that integral sign, which means I'm going to have 6 times whatever my antiderivative is. So let's look at sine. Sorry, my 6 is going to be here. And I need the antiderivative of sine. So what do I have to have started with so that when I took the derivative of it, I got sine? Well, that's got to be a cosine. Question is it a positive cosine or a negative cosine? When I take the derivative of cosine, I get a negative sine. Okay, so then I had to have started with a negative cosine so that when I took the derivative, I would get a positive sine. And I still have 2x. So when I take the derivative of negative cosine 2x, I'm going to get positive sine of 2x times the derivative of the inside. I really am going to have the derivative of the inside here, but I don't have the derivative of the inside over here. There's no other constant in there, which means I can approach this 2 different ways. I can either rewrite this sine of 2x. What I really want to have is the derivative of the inside as part of my dx, so to speak. So I really want to have a 2 in here. But I can't just randomly throw in a 2, but I can randomly throw in a 1. So if I want to multiply by 2, but I don't want to actually multiply by 2, I want to multiply by a 1, I need to multiply by a 1/2. So I can think about it this way. The green things, when you multiply those together, they are just a 1. So I can multiply anything I want by a 1. Now this 2 is part of my dx. That's actually because it's the derivative of the inside, and I need to have the derivative of the inside, which means over here in my antiderivative, that 1/2 is coming with me. So the other way to think about it is, once I start with my antiderivative, I need to think about when I find my derivative. So starting with just this part, when I find my derivative, I'm going to have negative 6 times negative sine of 2x times 2. But that 2 isn't there, which in my what I'm finding the antiderivative of. There's no 2 in there. That's extra, which means to balance that out so I no longer have that 2, I would need to divide by 2. And again, it doesn't matter which way you think about it, but somewhere along the lines, you have to divide by 2 in your antiderivative. So the antiderivative ends up being negative 6 cosine of 2x divided by 2. I would just put it with my constant right there, plus c. So it's negative 3 cosine of 2x plus c is my final answer. And again, we can check that. Every single antiderivative you should be able to check. So that's negative 3. The derivative of cosine is negative sine of the same times the derivative of the inside. The inside is 2x, so the derivative is 2. Simplify that, it's 6 sine of 2x. And is that what I started with? Well, oops, all the way over here. It is. That's exactly what I started with. Next one, we're doing an e to the x. So, evaluate the antiderivative of e raised to 2x. Let's think about the derivative. If I have e raised to the x, the derivative of that is e raised to the x. What I do need to take into account is this 2. I'm not taking e to the x, I'm taking e to the 2x. So now I'm going to have e to the 2x. But when I go backwards and I take the derivative, I'm going to end up multiplying by 2, but there's no 2 there. So I also need to have a 1/2. To look at it another way, I have the antiderivative of e to the 2x dx. The derivative of the inside needs to be right here. And my inside is 2x. That derivative is 2. But again, I can't just randomly throw in a 2. I can only randomly throw in a 1. Multiplying by a 1 doesn't change anything. So if you look at this, the greens multiply to a 1, so everything's fine. The 1/2 stays. The antiderivative of e to the 2x is e to the 2x, and then add on your plus c. So whichever way you want to think about finding your antiderivative is fine. It doesn't matter. But let's go ahead and do our check. So I check. My 1/2 stays. My e to the 2x, the derivative of that is e to the 2x times 2. And my 1/2 and my 2's multiply to give me a 1. And I'm left with e to the 2x, which is what I started with. Onto the back. So now we have the antiderivative of 5 raised to the x. Let's refresh our memory. We just refreshed our memory on this because we had this on the test. Y equals 2 to the x. What's my derivative? The derivative, of course, is 2 to the x times the natural log of 2. So I need to remember that when I'm dealing with this antiderivative of 5 raised to the x. Now, this natural log 2 is a constant. It's just a number. It's a constant. So we can look at this two different ways. I'm going to end up with a 5 to the x, but when I take my derivative, I'm going to get 5 to the x times natural log of 5. But there is no natural log of 5. So I need to balance that out by dividing by natural log of 5. Now, that didn't make sense. Let's look at the other way. I have the integral of 5 to the x dx. When I take the derivative of 5 to the x, I'm going to get a natural log of 2. That's constant. I can throw that in. I can't just throw it in really though. I can multiply by a 1. So if I multiply by natural log 2, I also need to multiply by 1 over natural log 2. Now when I take my antiderivative, the 1 over natural log 2 stays. The antiderivative of 5 to the x is 5 to the x plus c. Except that I multiplied by natural log 2. Apologies everyone. This should be natural log 5. Not sure. I'm stuck on the example that I did. So I apologize. This should be a natural log 5. This should be a natural log of 5. And this should be a natural log of 5. Sorry for the confusion there. Okay. And again, whichever way you want to think about is fine. So let's do a check. So 1 over natural log 5 is a constant, so I can pull that out. The derivative of 5 to the x is 5 to the x times natural log of 5. Then I have a natural log of 5 on the top, a natural log 5 on the bottom. Those become a 1, leaving me with 5 to the x, which is what we started with. Next one. Okay, this is where it gets a little bit tricky. Now, the derivative of the inside for this one, my inside is x squared minus 3, which means the derivative of the inside is going to be 2x. Now, I can multiply by a 1 anytime I want, as long as only constants are involved. I may never, ever, 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 ever multiply by a 1 involving an x. I can't do it. An x could be 0, and I can never multiply by a 0. I can never divide by 0. X is a variable. I can never multiply by an x. Don't know where my screen just went. So, sorry about that. What we need to do for this one is we need to actually multiply this out. Okay, we're going to square this out, then find the antiderivative of each term. So the antiderivative of x squared minus 3 times x squared minus 3 dx. So multiplying this out, I get x to the 4th minus 3x squared minus 3x squared plus 9. Okay, go ahead, pause the video anytime. If it's going to take you a little bit longer to do that, and it's fine. X to the 4th minus 6x squared plus 9 dx. And from here, we're just going to find the antiderivative of each term. So I have x to the 5th. I add 1 to the exponent and divide by the new exponent. Minus 6x, I I add 1 to the exponent and divide by the exponent, plus 9x plus c. And I can simplify that if I want, but that is our antiderivative. Now, example 6 is a little bit different. It looks almost exactly the same, but there is a little change. Let's go back to my inside. My inside is x squared minus 3, and the derivative of the inside is 2x. But look at what is actually in my antiderivative. I do have an x. So the only thing I'm missing from the derivative of the inside is the 2. So thinking this through, we're going to end up with something was raised to the second power, which means I'm going to end up with something raised to the third divided by 3. I add 1 to the exponent and divide by that. X squared minus 3 is that something. Now, when I take the derivative of this, my exponent's going to end up coming down, which is going to simplify with this 3 down here. My exponent will then become 2. Then I multiply by the derivative of the inside, which is 2x. The x is right here, but I'm missing my 2, which means I'm going to end up having a 1/2 to balance out the 2 when I take the derivative. So that's a little bit messy looking. We have x squared minus 3 raised to the third divided by 3 plus c, which of course can be simplified to 1/6 x squared minus 3 cubed plus c. So let's look at it the other way. I have the integral of x squared minus 3 squared. I'm going to move the x so it's over here with my dx because it's actually part of my derivative of the inside. But again, the derivative of the inside was 2x, so I need a 2 right there. I can't multiply by a 2. I can only multiply by 1, so 1/2 needs to come on the outside. So I end up with 1/2 times x squared minus 3 raised to the third, divide by that new exponent, plus c, and we end up with the same thing, 1/6 times x squared minus 3 cubed. So let's go ahead and check it. And when I check it, the constant stays. I bring my exponent down using the power rule, 3 times x squared minus 3, which is now raised to the second power, times the derivative of the inside, which is 2x. And let's do a little simplifying. 3 times 1/6 is really 1/2. And I have my x squared minus 3 squared times 2x. And then the 2 and the 1/2 reduced to a 1. I'm going to pull the x in front, and then I have x squared minus 3 squared, and this, sorry, I'm all over the place, is the same as what we started with. So, antiderivatives, please bring any questions that you have to class. We'll be practicing quite a few of these, and have a nice evening.